In the last lecture, we were considering the various characteristics and implications of the properties of the system function HFS, which is defined as the ratio of the Laplace transform of the output to the Laplace transform of the input with the zero initial conditions in the system. When we say zero initial conditions in the system, we don't really end up with any laws of generality, because any initial condition in the system can be replaced by an equivalent source, as we have thought of in the case of electrical networks, and similarly in the case of systems as additional inputs. We can think of non-zero initial conditions as additional inputs, and therefore each non-zero initial condition can be thought of as a separate excitation, and one can use the superposition principle. Therefore, when we say zero initial conditions, there is really no laws of generality. We considered various aspects of the characteristics of HFS. Now let us start with consider once again the free response of the system as given by the poles of HFS. We said in the last lecture that as far as the output is concerned, it consists of two parts, one which corresponds to the poles of XFS and one which consists of the poles of HFS. The poles of XFS give rise to the forced response part of the output, and the poles of HFS will give the part corresponding to the free response of the system or the natural response of the system. And the poles of HFS are indeed the zeros of FFS, which is the denominator of the polynomial in the denominator polynomial in HFS. Now, depending on the location of the poles of HFS, we have different types of behavior. So in the complex plane, if this is the complex plane, S plane, suppose I have a pole here at the location A, then that corresponds to, in the partial fraction expansion, k over S plus, this is minus A, let us say, k over S plus A, and this will give rise to a response k e to the power of minus at. So that is something which decays with time. On the other hand, if I have a pair of complex conjugate poles here, say at locations B, say this is A, at the location B, this will give Ks plus say m divided by S plus alpha whole squared plus omega naught squared. That will be the type of expansion, the partial fraction expansion that you get corresponding to the locations in the B positions, where this is minus alpha and this is omega naught. And that gives rise to a response which is some, say, a e to the power of minus alpha t sine omega t plus beta, which means that you are having a decaying oscillations with the amplitude decaying exponentially. On the other hand, if you are having a pair of poles on the imaginary axis, location C, that corresponds to something like Ks plus m once again over S squared plus omega naught squared, and this gives rise to a response which is sine omega naught t plus beta, which is sustained oscillations. Therefore, the poles of HFS dictate the natural response of the system. On the other hand, if there is a pole in the right half plane, suppose there is a pole here, that corresponds to, suppose this is D, S minus D, then this corresponds to k e to the power of dt, and that is represents an increasing exponential which indicates instability. So one can say that if the system is stable, if you have a bounded input giving to raised to an XFS which is finite, then the natural response must decay with time, or at least stay steady with time. It should not take off, it cannot go indefinitely to large quantities. Therefore, for stable system we require all the poles of HFS to be in the left half plane, and as a borderline they can be on the imaginary axis, because that is the limiting behavior. However, what happens if the poles are repeated? Repeated poles really mean that in the denominator polynomial HFS, you have factors like S plus alpha whole squared, or S squared plus omega naught squared whole squared, or s plus alpha squared plus omega naught squared whole squared if the repetition is of the order 2. So let us consider what happens if you in the complex plane you have a pole of order 2 here, that means multiplicity 2, a repeated pole. It can be repeated 2 times, 3 times and so on, but let us illustrate it for the case of 2. That means in the partial fraction expansion here you have k over s plus alpha whole squared, and the time domain response corresponding to this will be at the form kt e to the power of minus alpha t. So that means you have it exponentially decays but starts with 0 amplitude. On the other hand, if you are having 2 complex conjugate poles repeated like this, that will be of the form some f of s over s plus alpha whole squared plus omega naught squared whole squared. That means these 2 complex conjugate poles are repeated twice, and this gives rise to a response which will be once again this envelope, it will be like this. So even though the poles are repeated they are in the left half plane, it gives us a stable response. The response ultimately decays. What happens if there are repeated poles on the imaginary axis? Suppose there are order 2. So this corresponds to a term like f of s over s squared plus omega naught squared whole squared, and this gives rise to a time response which is some kt sine omega t plus theta. That means the time response corresponding to that would be something like this. So this certainly should be excluded if we want a stable system. If we have a reasonably well behaved bounded type of input, the output cannot grow indefinitely large for a stable system. So that means we cannot have repeated poles on the imaginary axis. Certainly we cannot have poles in the right half plane, whether it is repeated or simple, and on the imaginary axis we cannot have repeated poles. Even repetition of by an order a duplication of poles, that is multiple rows order 2 themselves are not permitted. Certainly higher order poles cannot be permitted. But as far as the left half plane is concerned, what we have illustrated for order 2 can also be extended for higher order. That means you can have a pole on the negative real axis of order 4, 5, 6, whatever it might be, and similarly complex conjugate poles in the interior of the left half plane can be of any order whatsoever. Ultimately the response will decay. On the imaginary axis, however, you can have only simple poles. That means, to conclude this discussion, if we want to have the free response to decay with time, then we require that the poles of HFS should be in the left half plane, in the interior of the left half plane. If they are on the imaginary axis, they must be simple. They must be of unit multiplicity. They cannot be repeated. And certainly we cannot permit poles of any order in the right half plane. So that is the meaning of the stability. So if the system is stable, a bounded input must give rise to a bounded response, and so the response cannot go on, cannot take off to infinite limits. It can't grow indefinitely with reference to time, and the requirement therefore is that the poles should be in the left half plane. If on the imaginary axis, they should be simple. Let us now look in some detail the forced response characteristics of the system. We know that y of s equals h of s times x of s. Now we will take a particular case of x of s, which is of the form xt is a e to the power of, say, s naught t. That is an exponential signal. Then it gives rise to a forced response y of t, which we have already seen in our preliminary lectures. Y of t will be h of s naught times a e to the power of s naught t, which means this is h of s naught times e to the x of t. So whenever x of t is of an exponential type, exponential signal with a complex frequency s naught, the forced response is obtained merely by multiplying x of t by h of s evaluated at that complex frequency. Hs, s, you substitute s naught for s, and that is what you get. This is something which we have already discussed. Let us see how it arises. We know that if xt is a to the power of s naught t, y of s will be h of s times the Laplace transform of x of t is a divided by s minus s naught. So in the partial fraction expansion of this, you have one term corresponding to s minus s naught, which is h of s naught times a, plus terms corresponding to poles of h of s. So there are other terms which correspond to poles of s. They give rise to the free response. The forced response is given by this. This gives you the forced response. And so from this, y of t, the time domain representation of this is a times h of s naught times e to the power of s naught t. So that is what we are having. That's exactly what we said is the forced response. So this is how it ties up with the Laplace transform theory. What we already know from your preliminary lectures, whenever an exponential signal is there, the output, the forced response is the input times h of s naught. Now, arising out of this, we can talk about the frequency response characteristics. Suppose you have e to the power of j omega naught t as the input quantity. Then we know the forced response of this. The forced response of the system, y(f) of t, this is x of t. The forced response is h of j omega naught e to the power of j omega naught. So this is the frequency response function. But we are often interested not in exponential signals of the type e to the power of j omega naught t, but something like cos omega naught t, let us say. So cos omega naught t, we can take this as a real part of e to the power of j omega naught t, and therefore the response to that would be the real part of h of j omega naught times e to the power of j omega naught t. So this can be written as, if h of j omega naught as a magnitude h of j omega naught, so h of j omega naught magnitude times some phase. So the magnitude of this is h of j omega naught cos omega naught t plus an angle which is the angle of h of j omega naught t. So that will be what you are having. So depending upon, if cos omega naught t is the input quantity, the output quantity is given by the magnitude, is magnified by the magnitude of the frequency response function. The phase is increased by the the angle of the frequency response function, cos omega naught t plus angle of h of j omega naught t. Similarly, if you have sin omega naught t, the forced response will be h of j omega naught sin omega naught t plus the angle of h of j omega naught. So this is the frequency response function. We have talked about this when we discussed the Fourier transform and Fourier series, Fourier methods, and there h of s substitution s equal to j omega will give the frequency response function. So we can see how this ties up with our Laplace transformation theory. To summarize then, what we have talked about is the total response with zero initial conditions. If the input is delta t, it gives rise to h of t. And the Laplace transform of that is h of s. The Laplace transform of the output is h of s. If the input is ut, I'm sorry, not this, it's only the arrow, this is the input, this is the output. We call that the initial response or step response at, and we indicated this as as. That will be h of s over s. So we have a general xt. Then in terms of The impulse response we say is xt convolved with ht, which in Laplace transform domain is xs times hs. We can also have alternately x dash t convolved with at. The convolved with at, that is the step response. The meaning of this is x0 plus at plus 0 plus 2t of x dash t x dash tau at minus tau d tau. All this we discussed in the last lecture. So in terms of Laplace transforms, we can write x of s times s. We also have an alternative representation of this. If you recall, you can write this as a dash t convolved with x of t. That also has the same Laplace transform. And in these two expressions, a dash t and x dash t, we are talking about the situation we take t starting from 0 minus, starting from t greater than or 0 minus. So that is what the total response of a system can be obtained from the either the step response or the impulse response, or in general terms, this is how these equations will run. Now let us talk about set up a similar table for the forced response. So if the input is an exponential signal a e to the power of s naught t, the forced response is h s naught times e to the power of s naught t. If it is the e to the power of j omega naught t, it is h j omega naught e to the power of j omega naught t. And if it is cos omega naught t, it is h j omega naught magnitude cos omega naught t plus the argument of h of j omega naught. So h of j omega naught is a complex number, and whatever angle that it has got, that is the addition to the phase of the cosine function. Sin omega naught t, this will be likewise h j omega naught magnitude sin omega naught t plus the argument of h of j omega naught. And h of j omega is called the frequency response function. Which we had used in steady state sinusoidal analysis, circuit analysis. After all, h of j omega is something like your impedance z, y, and all related to h of j omega. Z is a function of omega, h of j omega is a function of omega. So impedance is the ratio of voltage to current. So if you take the voltage, the response quantity, and the current as the input quantity, the system function corresponding to that is z in the normally what we talk about z is a system function in this context. Let us now work out an example to illustrate these ideas. Let us now consider this example where we have a network which is linear time invariant, and we treat this as a system. The input is this whatever voltage you give, and the response quantity is identified as the current IT. So when the switch is closed at t equals 0 in this particular network, it is observed that the current that flows into the network is given by this 4 e to the power of minus t minus 3 e to the power of minus t minus 2t for t greater than 0. Of course, it goes without saying that IT is 0 for t less than 0. Given this data, you are asked to find impulse response of the network. That means if the excitation is a unit impulse, what is the corresponding output? system function. Taking the input voltage as the input and the resulting current as the output. See, response to an input which is e to the power of minus 4t ut. D, steady state response to an input sinusoid cos 2t. Suppose a sinusoidal voltage is given to this network, what kind of steady state current you would get in this terminals? That is the question that is asked. So all these quantities are to be obtained. Now, the input is 1 volt and the output is 4 e to the power of minus t, 3 e to the power of minus 2t. Therefore, the input Laplace transform is 1 volt. So 1 volt is given at t equals 0 to this network. Therefore, it is a step function really. V of s is 1 over s. The current in the network as the Laplace transform of this is 4 upon s plus 1 minus 3 upon s plus 2. 4 upon s plus 1 minus 3 upon s plus 2. That is the expression for the current. Therefore, I of s over V of s is the system function h of s that will be obtained as, you can work this out and show that this is equal to s times s plus 5 divided by s plus 1 times s plus 2. You can show that this is the system function h of s. So that is the answer to B, which we have already obtained. If you look at this I of s can also be thought of as a step response because the input is one unit step. Therefore, A of s is simply this one. So it is s plus 1 times s plus 2. So 4s minus 3s is s, 8 minus 3, 5. So this is A of s. You can see that h of s is s times A of s. That is a result which we already know. Impulse response h of t is the inverse Laplace transform of h of s. This is h of s. So h of s can be expanded by means of partial fraction expansion. So it will turn out to be 1 minus 4 over s plus 1 plus 6 over s plus 2. So if this rational function, make the partial fraction expansion of this rational function, you get this because the numerator and denominator are the same degree polynomials, s squared divided by, so the ratio of the two leading coefficients is 1, that is the first term, and then you have the residue for the pole at s equals minus 1 and the pole at s equals minus 2, it will be like this. So if you take the inverse Laplace transform of this is delta t minus 4 e to the power of minus t plus 6 e to the power of minus 2t, of course ut, you can write this 4 e to the power of minus t ut plus 6 e to the power of minus 2t ut. That is the impulse response. Now, response to e to the power of minus 4t ut. So x of s, the input is e to the power of minus 4t, this is 1 over s plus 4. So y of s corresponding to this is 1 over s plus 4, that is x of s, times h of s. H of s is s times s plus 5 divided by s plus 1 times s plus 2. That is the y of s. So you make the partial fraction expansion of that. So C continued, y of s turns out to be minus 4 upon 3 over s plus 1 plus 3 upon s plus 2 plus minus 2 upon 3 over s plus 4. That is, the partial fraction expansion of this will contain 3 terms. Those are the 3 terms. So yt will be minus 4 by 3 e to the power of minus t plus 3 e to the power of minus 2t minus 2 by 3 e to the power of minus 4t times ut. The input is e to the power of minus 4t, and the output containing this term e to the power of minus 4t, this is the forced response. The forced response contains exactly the same complex frequencies as in the input. The system function has got 2 poles at minus 1 and minus 2. Corresponding to this, you have got these 2 terms, e to the power of minus t, e to the power of minus 2t. So this corresponds to this poles of x of s. So this represents the natural response or the free response of the system. So as we mentioned earlier, the Laplace transform theory enables us to get the total solution in one step, the free response part and the forced response part. You can get y of t using convolution integrals also. Now that you know ht and also you know this itself, the it itself is at, you can use the convolution and find out yt either from the impulse response or the step response, and you end up with the same result. That you can work out as an exercise. Now it will be interesting to see whether you can get the forced response independently. Suppose you wanted only the forced response. So the input is e to the power of minus 4t. So the forced response of that is h s naught, where s naught is minus 4 times the input e to the power of minus 4t. So if you substitute, this is really h minus 4 e to the power of minus 4t. We know h of s is s times s plus 5 divided by s plus 1 times s plus 4. So when you substitute minus 4 in this for s, you get minus 4 s plus 5 1 divided by minus 3 times minus 2. So that will become minus times e to the power of minus 4t. That becomes minus 2 upon 3 e to the power of minus 4t. So this is exactly what you got here. So verification of the forced response, you can see that the forced response can be obtained by substituting s naught for s, where s naught is the complex frequency present in the input exponential signal. The last part is, what is the steady state response for cos t? Cos 2t. So the sinusoid has an input sinusoid has a frequency 2. So hj2 equals, our h of s is s times s plus 5 divided by s plus 1 times s plus 2 with the substitution s is equal to j2. So when you substitute s equal j2 in this, you get j2 times 5 plus j2 divided by 1 plus j2 times 2 plus j2. If you simplify this, rationalize and simplify this, this will turn out to be approximately 1.7 at an angle of 3.4 degrees. So when you substitute this j2 for s and evaluate this, the frequency response function hj2 turns out to be 1.7 times 3.4. So if cos 2t is the input, the steady state response of that will be 1.7. This is the magnitude of the frequency response function, cos 2t plus 3.4 degrees. So this frequency response function, it tells us how the amplitude of the sinusoid, how the phase of the sinusoid are modified in the, as far as the steady state response is concerned. If it is sin 2t, it would still be 1.7 cos sin 2t plus 3.4 degrees. So this is how one can use the frequency response function to evaluate the steady state response with sinusoidal driving forces. In the course of the last four lectures, we have seen how the Laplace transform method can be profitably employed to solve for the transients in networks and systems. Taking the case of network transients, to be specific, we saw that in the Laplace transform method, how the governing equations for the network in question are formed in an algebraic form, either from the transformation of the differential equation or to the transform diagram, and how the response quantities, the Laplace transforms of the response quantities can be algebraically arrived at, and therefrom through the inverse transformation how the corresponding time functions can be found out. There is no algebra involved. Furthermore, there is no calculus involved, there is only algebra that is involved. Furthermore, the initial conditions are plugged into the formation of the algebraic equations even at the very beginning itself, and no separate evaluation of the arbitrary constants is called for, as we had in the case of differential equation approach. Perhaps the greatest difficulty in the solution of by the Laplace transform method lies in finding out the inverse transformation, particularly when the denominator polynomial is of a high order. Not only we have to find the residues for the various poles, but the determination of the poles itself will become tedious if the denominator polynomial is of high order. But this is a problem which is attendant for large size problems in any method, even in the differential equation approach, and certainly the blame cannot be laid at the door of the Laplace transformation method. We have also seen how this system function can be used to evaluate the performance of a general system. The system function embodies in itself various properties pertaining to the system. We can use the system function to find out the steady state response to an exponential input by mere substitution of the corresponding complex frequency for S in the HFS. We can see how the system function can be used to find out the impulse response. We can find out how the system function can be used to find out the step response, and how the system function is almost equivalent to the frequency response function. So the system function has a number of versatile properties which we have seen, and in a general situation we can see how the system, how we can, once we know the frequency response or the impulse response or the step response, we can find out the frequency response. Conversely, if you know the frequency response over a large entire range of frequencies, there are also methods available by means of which you can find out the transient response. In other words, in linear systems, if you know the transient response, by that I mean the response to a step input or an impulse input, we can find out the frequency response for any sinusoidal input, and vice versa. There are algebraic procedures and graphical procedures available where analytical expressions cannot be found out for either the frequency response or the transient response. After having said all this, the Laplace transformation method, we must also say, has some disadvantages. Certainly, it cannot be used for systems which are either nonlinear or time varying. Even for the simple case of the product of two time functions, the corresponding Laplace transform cannot be easily found out. It involves complex convolution. For other types of nonlinearities, it may even be difficult to find the Laplace transformation. Similarly, when you have a time varying situation, the convolution integral that we have talked about cannot be used in the same form. It becomes much more complex. So for the general nonlinear and time varying systems, Laplace transformation is almost useless. The differential equation is more fundamental, and perhaps it may furnish the only feasible method of solution in such situations, even though this may involve complicated calculations and perhaps even numerical methods for the solution. But then the differential equation method is more fundamental, and it can be used for a general situation, whereas the Laplace transform method cannot be used in such situations. So with that, we close our discussion of the application of Laplace transformation method to networks and systems, and now we will look at some problems which form an exercise on the topics that we have covered in the last 4 lectures. In the first 3 problems in this exercise, we find the transients in a circuit of the operation of certain switches. So we assume that in problems 1 to 3, assume that steady state conditions are reached before the operation of the switch S. So whether the switch S is opened or closed in the first 3 problems, we assume that before the operation of the switch, the conditions in the circuit have reached steady state. So that will enable us to find out the conditions at t equals 0 minus in the various circuits that we are going to investigate. First problem. So in this problem, you are having a 12 volts DC source connected to a circuit consisting of a 4 ohm resistor, 2 Henry inductor, a 2 farad capacitor in shunt, another 2 ohm resistor and a 1 ohm resistor. Now this switch S is kept closed for a very, very long time till steady state is reached, and then it is opened at t equals 0. Now you are asked to find out the capacitor rate of change of capacitor voltage dVc dt, d squared Vc dt squared, the third derivative d cubed Vc dt cubed, not as a function of time, but all of them evaluated at t equals 0 plus. And how do you do this? Using Laplace transform method. So we are not interested in the time domain behavior of Vc or the derivatives. We are interested in the values of the first, second and third derivatives of the Vc evaluated at t equals 0 plus. Now if we have to do this in the classical differential equation approach in time domain, it becomes a little tricky and complicated. But the Laplace transform method gives us a very simple way in which we can calculate this, and this problem illustrates that technique. So all you have to do is, using the t equals 0 minus conditions of Vc, set up the transform diagram for this and arrive at the expression for Vc of S, the Laplace transform of the capacitor voltage. Once you have the Laplace transform of the capacitor voltage, you can also find out the Laplace transform of the derivative of the capacitor voltage, the second derivative of the capacitor voltage, third derivative of the capacitor voltage, all in Laplace transform domain. But you don't have to find the inverse Laplace transform to evaluate Vc or Vc prime, Vc double prime or Vc triple prime. Only once you have got the Laplace transforms of the respective quantities, you apply the initial value theorem and find out their values at t equals 0 plus. So this is an application of the initial value theorem. So as we said, the initial value theorem will always give you the t equals 0 plus values. So you have to apply that theorem and find out the respective values. You don't have to find the inverse Laplace transform of any one of these quantities. Second problem is this, in which we have a 2-loop circuit consisting of an inductor and a capacitor and so on. The switch is kept closed for a very, very long time. That enables you to find out the initial conditions with respect to the capacitor as well as the inductor, and you use them in the transform diagram. 4 volts, 1 ohm, 4 farads, 1 ohm, 4 henries, and you are asked to find Vc of t for t greater than or equal to 0. Use 2 methods. Once you have the transform diagram, you analyze the transform diagram on the loop basis using the loop current method or the node voltage method, and you get the solutions for Vc of t by both methods and compare. Both should be the same. When you are using the node voltage method, as I mentioned, when you replace these initial conditions on the capacitor by means of an equivalent source, it is the voltage across those 2 nodes which represents the capacitor voltage in the transform domain. So you keep that in mind in calculating the capacitor voltage using the node voltage method. So this is an exercise in using the transform diagram for the solution of one of the response quantities, which happens to be Vc of t in this particular example. So you can take this down. Now the third example concerns the use of the transform diagram approach where mutual inductance are present. So you have a 3 volt source connected to a series circuit of 1 ohm and the primary coil having this inductance, self-inductance of 1 Henry. It is coupled to a secondary coil of 4 Henry self-inductance through a mutual inductance of 1 Henry. This is the mutual inductance, this is a self-inductance of coil 1, this is a self-inductance of coil 2, and the secondary circuit is close to a 2 volts DC cell, DC source and a 2 ohm resistance. So this is the situation, and so when the switch is kept open, naturally only current will flow through this, there will be no current here. So I2 0 minus you can find out and put appropriate initial conditions in the transform diagram. And once the switch is closed, of course this circuit is also completed. You have got a current here and a current there, and you write down the appropriate loop equations and solve for I2 of S. From that, find I2t for t greater than 0. So you have to use the replacement of initial conditions in coupled coils by equivalent sources. You can use either current sources or voltage sources and find out the appropriate solution. Problem number 4, we have a series circuit containing a resistance R of 1 ohm and a capacitor of 0.5 farads, and this is connected to a voltage source Vs, which has got a discontinuous character. It's a set of periodic pulses. And so on and so forth. This is the variation of Vs. It has, the pulses have an amplitude of 10 volts. This is t in seconds. So it's a pulse frequency is 1 hertz, and the pulse duration in each period is half a second, 3/2, 2, and so on and so forth, 2.5, etc., etc. So this is the VFS, and assume that if this is the capacitor voltage, Vc0 minus is 0, that is the pulse is applied at t equals 0, first pulse, at that time the capacitor voltage is 0. Now you are asked to find out the current. So you are asked to find out an expression for the current in the network on the application of the discontinuous voltage source. This is a periodic voltage source starting from t equals 0. So you must find out the Laplace transform of that, use that, and get an expression for IFS, and you interpret the IFS. You will have e to the power of s factors also in that. When you find out the inverse Laplace transform, you get some delayed versions of certain quantities. You interpret them suitably and give an expression for I of t in the final expression, in the final result. Fifth problem involves the application of some of the system concepts that we have been talking about. So let me write this down. The response of an initially relaxed linear time invariant, that means constant parameters, system to a unit impulse delta t that is applied at t equals 0 is 4 e to the power of minus t ut. That means this impulse response of the system is given, and you are asked to find a series of quantities. Find the response of the same system that is once again assuming it to be initially relaxed to a unit step using time domain analysis. That is, you try to find out the convolution of the step and the impulse response. B, find the response to e to the power of minus t ut in time domain, that is, don't use Laplace transform. Find the response to this in time domain using impulse response as a reference. So you use the convolution integral using h of t. Then C, find the solution in B using the step response. So in time domain, once again, you use the convolution integral involving this initial response A of t. D, find the system function h of s. E, using the system function h of s, find the responses in A and B. That is, use the Laplace transform method this time. Earlier you were using the convolution integrals. Now using h of s, find the response in A and B and compare, of course. Compare with the earlier results. F, find the response of the system to an input sin 2t ut. So if the input is a sinusoid applied at t equals 0, find the response of the system to this input. Of course, you can use Laplace transform method for this, quite convenient to use. G, find the steady state response to this input sin 2t without using the result in F. So you are asked to find out the forced response of the system sin 2t. The forced response is with an input sin 2t also happens to be a steady state response, because it's a steady, this sinusoid is a steady state, has a steady state characteristic. It doesn't diminish with time, the amplitude is maintained. Therefore, the forced response to sin 2t is also the steady state response, and that portion of the total response that you obtained in F, you obtain independently using the frequency response function and compare with the result in F. That means whatever in the total response, the particular portion corresponding to the steady state behavior must agree with this. Compare with the result in F. Then lastly, H, find the input xt which when applied to a system yields a response sin 2t ut. So what you want is you determine what type of excitation should be given to the system so that the output is sin 2t ut. That means it must start from 0 like this. So that is the output. So what type of input should be obtained in order to find out, get this output? So this last problem illustrates the ideas of system, the use of Laplace transform to the system analysis that we have discussed in the last 2 lectures. It is quite a comprehensive package of questions that we are having. It covers more or less all the aspects that we have discussed.